Okay, so for this podcast or screencast, we're going to cover ventilation perfusion coupling, just in case anybody was confused about that, and then briefly go over the graphs with hemoglobin and oxygen. So, first up, ventilation perfusion coupling. So, the idea here is that what your lungs are trying to do is match blood flow and airflow. So perfusion is blood flow, and you're trying to make sure that the blood is flowing where there's lots of ventilation or where there's lots of oxygen. And it's really oxygen that's in control here, so that's what you want to concentrate on. In this situation here, we have an alveolus that is somewhat deflated. It doesn't have good ventilation, which means there isn't a lot of oxygen there. This decreased partial pressure due to oxygen is sensed by the arteriole through a process called autoregulation. And when the arteriole senses that oxygen levels are dropping, the smooth muscle in that arteriole will constrict, and you will then send less blood to an alveolus or a region of the lungs where there's less oxygen or less perfusion. So over here, you have not very much air, but lots of blood. So you send less blood where there's less air so that you match over here, you have not very much air and also not very much blood. In the next slide, we have the opposite situation. Here we have an alveolus that is fully inflated, so it's going to have good ventilation, which means increased partial pressure due to oxygen. When the arteriole senses increased oxygen levels or increased partial pressure due to oxygen, it dilates and you get dilation of the arteriole, which then leads to increased blood flow or increased perfusion where there is increased ventilation. So that's all it's about, is if there's lots of oxygen, you dilate the blood vessels. If there's less oxygen, you constrict the blood vessels to match blood flow with airflow. So the next topic is the relationship between hemoglobin and oxygen, or the affinity of hemoglobin for oxygen, how tightly hemoglobin is going to hold on to oxygen. And before you look at any of the graphs again and possibly get intimidated by the graphs, it's all kind of common sense. So you have oxygen, temperature, and pH that are all affecting the relationship between hemoglobin and oxygen. And they all do so in such a way that hemoglobin is more likely to let go of oxygen in highly metabolic tissues. So tissue where there's less oxygen, higher temperature, or lower pH, all of those conditions are going to lead to a decreased affinity of hemoglobin for oxygen, so that oxygen gets dumped off in the metabolic tissues. And that's really the heart of it. If the graphs confuse you, you can just ignore the graphs. So if you're looking at oxygen or partial pressure due to oxygen, increased partial pressure due to oxygen increases the affinity of hemoglobin for oxygen, or as it says down here, as PO2 levels drop, the affinity of hemoglobin for oxygen also drops. So it's not just that there's less oxygen bound to the hemoglobin because there's less oxygen around, but when there's less oxygen around, the hemoglobin is less likely to pick up or hold on to more oxygen. So if you want to think of it, or think of what's happening as you're moving from an area where there's lots of oxygen, like the lungs, to areas where there's less oxygen, like exercising tissues, as you move down the graph, that's decreased affinity, which means increased oxygen delivery to that tissue. So up here in the lungs, there's lots of oxygen, high affinity, so the hemoglobin is highly saturated. And then as you move into tissues that are resting, as it says right here, not highly metabolic, these tissues are going to have less oxygen than is in the lungs, but not dramatically less. Um, so as you move into those tissues, you can think of this as the amount of oxygen that hemoglobin is going to give up when it moves from this much oxygen to that much oxygen. Then, as you move from resting tissues into exercising tissues, because as you start to strip oxygen away from hemoglobin, hemoglobin becomes more likely to give it up, you get this real rapid decline. So in a resting tissue, hemoglobin unloads this much oxygen. And then as the blood moves into exercising tissue, hemoglobin unloads that much oxygen. So because the curve is really steep right here, it makes hemoglobin very sensitive to the oxygen levels in exercising tissue versus resting tissues, and ensures that more oxygen gets dumped off in exercising tissues than in resting tissues. And if you sort of move up the curve the other way, the other thing that this ensures is that when the blood enters the lungs and hemoglobin starts picking up more oxygen, it ensures that hemoglobin picks up as much oxygen as possible. So it encourages loading of oxygen in the lungs and unloading of oxygen in the exercising tissues. Temperature. Now you've got all of these different graphs, and it is easy to get confused by it. But you just need to remember that everything is set up so that highly metabolic tissues get more oxygen. So if you exercise, you overheat, because heat is a byproduct of metabolism. So those tissues that are more highly metabolic are going to be slightly warmer than other tissues that you're not using at that point in time. And then that is going to decrease the affinity of hemoglobin for oxygen, so that hemoglobin is more likely to release oxygen in warmer tissues. Excuse me, I'm still fighting that cold, and so I'm a little congested here. So if you just pick, let's say, and again, I should say that we've got the same graph. It's supposed to be partial pressure due to oxygen on the bottom and saturation state at the top. If you just pick one spot on the x-axis at any given partial pressure due to oxygen, as the tissue warms, as you go from 10 degrees to 20 degrees all the way up to 43 degrees, that change in temperature causes the release of all that oxygen. So as hemoglobin enters a tissue at 43 degrees, it's going to unload that much oxygen. And if the hemoglobin is running through a tissue at, say, 20 degrees, it releases just that much oxygen. So if you hold the partial pressure due to oxygen the same and just look at the different temperatures, higher temperature means lower affinity, more oxygen is being dumped into that blood, or excuse me, into that tissue. And then pH is the same. So as pH decreases, which is what metabolism does to your tissues, the affinity of hemoglobin for oxygen also decreases. So think now lactic acid, but there are other byproducts of metabolism that lower the pH, but lactic acid is the easiest one to remember. So those muscles that you're using are going to be producing more lactic acid than those muscles that you're not using. So those muscles that you're using are going to have a lower pH than other muscles. So again, if you just pick one point on the x-axis, or one partial pressure concentration or partial pressure reading for oxygen, and then compare the three graphs here. On this top one, you've got a relatively high pH of 7.6. And then as you move from a tissue with high pH to a tissue of lower pH at the same oxygen content, you have this much difference in the amount of oxygen that's attached to the hemoglobin. So as you move from the high pH tissue into the low pH tissue, you're dumping off that much oxygen just based on the pH change. So hopefully that makes things a little bit easier. A quick little review of a couple of things. Thanks for listening.